Hello and welcome to this Stryker session on cleaning. My name is Dr. Rod Parker and I'm the principal scientist at the Instruments Division at Stryker. I've been involved with this process for an awful long time and been involved with instructions for use for cleaning of medical devices for over 20 years. In that time, I've come up with many challenges that I've been exposed to, and during this session, I'd like to, put some of those out to you. Those being my top four, which would be pre-treatments, enzyme use, cleaning on actual clinical soil, and issues with powered equipment. Challenge number one, pre-treatment. Two major issues with pre-treatment are what does it do over the time it's applied, and when it's removed, is it removed effectively and efficiently? The results should show you how a pre-treatment improves your cleaning process. So what does Stryker have, understand anything about cleaning? Well, we have conducted time tests on very efficient hip surgeries, as you can see here. And what this study tells us is that drying on a surgical soil happens long before any application of pre-treatment can happen on the case. The standard does state, that gross soil should be removed during any case. So those aspects of soil that remain on a device should be wiped away. However, often these devices are used numerous times during a surgery, so it's not always practical that this soil gets removed immediately upon placed on the device. So we plan on these cycles being dried over 3 hours in a usual orthopedic case. So the paramount standard in sterile processing, at least in the United States, that we all know is the AAMI ST79. We may all be familiar with the process as it's stated here in the most recent version. That states that the action of what we have to do to prevent drying or hardening of the soil on a device. What we may often lose track of in the same standard is the need to ensure that the devices are being delivered to the processing area as soon as possible. In this slide, you can see the word minimize and underneath as soon as possible. There's no time stated requirement for what that means in the standard. To me, it means, as the section states, it should be processed as soon as possible. To further explore this, I've actually asked the Joint Commission on a time or the timing needed for a specific time frame. Often the length of 72 hours is spoken amongst conversations, and even with some Joint Commissioner investigators has come up as a time frame. The response from the Commission here clearly states that it relies on the manufacturer's instructions, the policy and procedures of the facility. I would stress that all facilities, all institutions have policies on routine processing, what you do every day, and a specific one addressing what is the delay, how long a delay has to be, and what do you do when you have a delay to ensure compliance with the Joint Commission's requirements. So as this site states, you have to ask your manufacturer of your pre-treatment for the data to support the question of moisture and treating your devices for helping the cleaning process. Your questions to the manufacturer should be: cleaning, does it help the cleaning? What data shows it? Rinsing, how effectively does it rinse away? Does it dry or lose its wetness? When does it rinse off? At the end of its effective time, and what data do you have to show it rinses free? Here's an example of some products I've tested. These is residue on a glass slide after 72 hours. These have been rinsed in hot water at 130 degrees F. And you can see, doesn't matter whether the product is moist or whether the product rinses away. As clearly evident in this slide, there is one product that has no residue and two others that have a various degree of different residues. If this process is supposed to help you with your cleaning, you want to make sure that the residue rinses completely free, as is evident by the one product in this slide. Challenge number two, enzymes, or what I like to refer to as the wild, wild west of the enzymatic cleaners. Enzymes need help. In conversations that I have with technicians on the bench, the underlying comment has always been that enzymes are required, or they're in some way magic. They always work, and they're better than any non-enzymatic detergent. The reality is that enzymes are catalysts. They assist with cleaning. They're a chemical process that moves one step from one stage to another. But you need to, make sure you're using the appropriate one to have a desired effect. The device manufacturers that require the use of an enzyme state in their instructions for use that they clearly need one. But enzyme manufacturers can also add important information. Here's another slide with a poster that's been presented from the global leader in enzyme production, the Novozyme company. As you can clearly see in this poster, it improves cleaning with enzymes. It talks about the situations, it talks about the study that they ran, and how that study clearly shows that the use of the right enzyme, the right amount of enzyme, and the proper production of an enzyme actually helps in the cleaning process. I know this one is a little bit hard to see, so if you need a cleaner copy, please go to the Novozyme website, and this is available there, along with any other information about enzymes and how they're made and how they're used. When you talk about testing, let's make sure we're getting the testing that we need to look at. This slide comes from a document that was prepared by a competitor for a cleaning product. This is not my study, but in this particular slide, you can see the test tells you that it's supposed to remove fatty soil from stainless steel in 3 minutes at 122 degrees Fahrenheit. And it's supposed to be used by the enzymatic detergent products. As you can see from this, there are many that work worse than water. And it's often funny that the Blue 62 product in here, which is a non-enzymatic cleaner, works comparatively well. It's a bit confusing for the detergents because 1, 2, 3, 4, and 5 contain proteases, which are not enzymes that remove fats or lipids. So what does this test actually show? It shows you that the fatty soil they used is Crisco with red food coloring. The agitation was with a stir bar, and it's suspended in only one way so that it can have flow patterns in removing anything. And the temperature was maintained on a hot plate with the beaker of a solution resting on it while stirring. When you repeat the test using a constant temperature at 122 degrees F with no agitation, you find the following. The key to good test is in the details. This tells us absolutely nothing in respects to the cleaning of an enzyme effect on chemistry. It does tell me that the Crisco melts at 122 degrees F without any agitation and returns similar results at more than not all the solutions. If you add agitation, then it comes almost all clean, but you get directional effects as well. We reran this test, and when you use our new enzymatic detergent E62, you're able to rinse off 100% of the fatty soil from the surface. It shows you that you have to be careful in what testing you get from the vendors versus the testing you need to ask for. We need to look at enzyme activity on actual clinical soil. Challenge is understanding how enzymes are used. Enzymes work to remove specific soils. Proteases remove proteins, lipases fats, amylases remove starches, and so on. Most healthcare considerations, we want to remove protein. Enzymes break down molecules into smaller pieces. They're carried away by the detergent. And just want to make point that those little missiles on the side, we're going to talk about those in a minute. Detergents use surfactants or surface activating agents, which is what a surfactant is, to attack the surface contact areas of a soil, lift the soil off completely. Note that that little missile is encapsulated in the surfactant portion of the solution, not in the enzymatic portion, which is why they were necessary in the previous slide for enzymatics as well. Enzymes can help, but you have to be using the right enzyme for the soil you want to remove. You need enough enzyme content in the water to effectively attack the amount of soil present. You must allow the enzyme to contact the surface and the soil for long enough of a period of time for the enzyme to break apart the molecule to work. Lastly, you need the best conditions for the enzyme to work. This slide demonstrates that in some enzymatic products, they stop working at a temperature cools down. Notice the temperature at 33 C is warm, if not tepid. This is an important consideration when looking at the long lumens, such as a flexible endoscope. Those temperatures are not going to maintain themselves the full length, and you need enough enzyme to be actively working through the whole length for the whole time. Challenge number 3, actual clinical soil. If we are using validated cleaning processes, why do we still have dirty devices? Is it because we have poor technique, devices that are just too complicated? Remember, all of them pass a validation. Or do we have faulty testing? Clinical soil is just actually hard to simulate for testing. So all devices, today have to pass a cleaning validation. They use test soils. These surrogate or fake soils, from a research perspective, are the best we can do. However, when you look at actual soils as a cleaning marker, the indications you get may not be what you expect. As you can see here in the clinical soil, even washed with water, when you compare the protein and hemoglobin numbers from those that it started with to the end point of when they were passing, only 3 of these would be considered not clean. So I don't think that anyone would allow any of the markers on the bottom or the slides on the bottom to be considered clean. But you have to understand that in a testing world, when you're looking at outputs such as protein and hemoglobin, making a number, passing by a number may not give you the full story. So it comes down to cleanliness as a focus of the degree of cleanliness, not necessarily whether it looks clean or not. In this particular slide, you can see with using a commercial detergent, every one of these slides passes a cleaning validation if you were looking at protein and hemoglobin as a number. But I don't think any of us would actually look at these visually and consider them to be clean. As we continue to test real clinical soil, we quickly find that test soils today are easier to remove and that more critical tests are required to judge the effectiveness of your cleaning process. We do know that your eyes are a pretty good, useful tool, and along with some simple magnification, can detect most unclean devices. But you need to test and verify that your cleanliness of a device can also help you in determining which cleaner you're going to use on real clinical soil. Challenge number 4, cleaning power or orthopedic devices, often referred to as the worst case. Powered equipment contains one of the highest diversities of materials of any medical device. Materials of construction are not conducive to long soaking times. And the use and cleaning of these devices requires that you have to move them repetitively. This is what I have the most experience with, and it contains a number of complexities. There's difficult areas to clean, as well as several types of materials, and they have to be placed into their respective areas and washed, sometimes repetitively, to get them clean. I'm a huge advocate of the results from users that have access to data performed by device manufacturers in their cleaning validations. You should be able to get this information from the device manufacturer. However, it has been a continual expressed problem with mine that the device manufacturers only test one cleaning product for manual and, if possible, automated. That's required of us from the standards. One of the many focuses, I believe, that's important to the cleaning process is you have to demonstrate that your cleaning chemicals don't remain on a device. This should be available testing. The testing should be available. If you rinse the device off, there shouldn't be anything left. This is what comes from your device manufacturer, and I think it's just as important that your solution manufacturer give you the same type of experience testing that they've done. At Stryker, we formulate cleaning products with the sole purpose for making cleaning better and easier. Since these chemicals are not regulated, what you see is what you get. So make sure you ask for what you need for your proof. The effectiveness of cleaning a device comes from the device manufacturer, not the solution manufacturer. Residues from those solutions and unrinsed chemicals can hurt your equipment, and in the long run, can hurt your patients. I hope this session has been informative, and I wish you success in all your cleaning efforts. Thank you for the time and attention, and good day.